Hi, and welcome back to our module on acid-base chemistry. Today we're going to talk about sources of acidity in the environment. So by the end of this video, you should be able to understand what is Chatelier's principle, and that principle should help you understand buffered pH systems and understand different sources of acidity in freshwaters. So if we just go back to our sort of USGS water quality cartoon, there's a lot of different ways that acidity can be sort of added to the environment, from point source pollution, like treatment plants or industrial plants up here, or fertilizer. And as part of this lecture, we're going to sort of try to understand why, when you add these acids to the environment, why don't they just immediately lower the pH to some really low level? And the crash course chemistry videos you watched earlier also do a pretty good job explaining this. So first, what's this Le Chatelier stuff? Well, it's a definition that applies to sort of any system at equilibrium. So I'm just going to read the Wikipedia definition. So when any system at equilibrium for a long period of time is subjected to a change in concentration, temperature, volume, or pressure, the system changes to a new equilibrium, and this change partly counteracts the applied change. And this is really critical for thinking about acid-base chemistry, and we'll talk about this a lot more next week with our video on carbonate chemistry. And basically this idea is captured fairly well in this plot showing the different chemical species that happen in the carbonate system. And so you may already know this, but CO2 can dissolve in water, and it can make bicarbonate, carbonate, or carbonic acid. And when it dissolves in, how much of it dissolves in water depends on the pH of the system. So let's say we have a system that is at this pH of 8. Well, then almost all of the sort of chemical speciation of this carbonate system is going to be this carbonate right here, HCO3 minus. So basically almost 100% of it is there. But now let's say I add some hydrochloric acid to the system and I drop the pH all the way down to 5. Well, the system is not going to sit there and not adjust. What it does is it'll shift all of almost all of this carbonate, and it'll shift it into the carbonic acid form, so this H2CO3. And so those will pick up hydrogen ions, some of them from the hydrochloric acid that we added to the solution. And so this sort of illustrates Le Chatelier's principle in an environmental setting, where if you change the pH of the system, you're going to change the concentration of these species in the system. And that really sort of is an important part of buffering pH systems, and also sort of a critical part of why freshwaters are able to handle some additional acidity, because there's all these buffered systems moving around, and you're not going to change the pH because you're just going to adjust the concentration of some of these carbonates or bicarbonates, for example. So we'll just kind of like focus on thinking about that buffered system. We can sort of think of it from the other way. What if you add more CO2 to the atmosphere? How is that going to alter freshwaters, or in this case, ocean water? Well, if you add more CO2, so we'll go back a slide. So let's say we added more CO2 to this system. What you're going to do is you're going to actually alter the pH, because you're going to dissolve more carbonic acid. And so when you dissolve more carbonic acid into water, if the pH is something like 8, you'll actually lower the whole pH of the system because you've added more of this. And so let's say when the ocean absorbs carbon dioxide from fossil fuel burning, that carbon dioxide will dissolve in seawater through this reaction, and that will release a hydrogen ion, so it'll release some acidity. And then sort of that reaction, some of that acidity can be absorbed by bicarbonate in the system, but not all of it. And so some of it might actually sort of change the pH of the system and actually extract carbonate from coral. And so that's why when we talk about climate change, we worry a lot about how it might have impacted coral reefs. This is actually an example of changing the acidity of the water and changing the carbonate equilibria through the addition of CO2. So that's one major source of acidity throughout all the environment, is just CO2 dissolving into water and forming carbonic acid. There's a lot of other forms that you can have acidity from carbon, but that's carbonic acid is an inorganic acid, so we also have a lot of organic acids. And organic acids are a really broad range of chemicals. They have a huge range of key pKa's, which means that some are really strong acids and most are quite weak. Many common ones that you already know and you consume every day, like citric acid or acetic acid, which is in vinegar. And many more you may have never heard of, like benzoic acid or oxalic acid. So we might ask ourselves, why is there such a huge range of these pKa's? Why is there such a range of acidity in organic compounds? And with this, this answer is mostly a lot of organic chemistry stuff that we're not going to go into detail on, but basically you can think about acidity in organic compounds with that resonance control is a major part. So how deeply integrated is the hydrogen ion that's going to contribute the acidity into the actual molecule? So is it on the edge, the outer edge of a molecule, or is it sort of like integrated in the main structure? You can also think about electronegativity. So how tightly bound to the different functional groups is the hydrogen ion, with it more electronegative holding the ion more tightly and therefore being less acidic, or orbitals. So what molecule is H plus bound to, and how, and on what orbital is it bound to the electrical charge, the negative electrical charge of that molecule? And we can see this a little bit with the dissociation of acetic acid. So this OH group here on the acetic acid, that's where the acidity comes from. And when you dissolve it in water, that leaves this group, and you have a negative charge over here, and then you make a hydronium ion over here, and that sort of is the sort of dissociation. And acetic acid is not particularly acidic. It's one of the sort of middle range of acidity for organic compounds. So there's a big range, and the key idea here is that the reason there's such a big range is that there's differences in the chemical compounds. And I just realized my video was blocking the compounds, so I'll just move it up for a second so you can see. But there's the hydrogen ion. Move myself back down. So I'm going to move myself up again. So the next source of major source of acidity in the environment is actually fool's gold. So fool's gold is called pyrite, and pyrite is just FeS2, and it's a major source of acidity globally. It's common in coal and hard rock mines, and it can also just be a common source of natural acidity in the environment. And the reason it's so acidic is that oxygen and water interact with FeS2 in the environment, and they immediately produce sulfuric acid. So sulfuric acid is a strong acid, and in hard rock mines, we go back to this image we've already seen, they can produce an enormous amount of acidity that can sort of turn the whole landscape this sort of red color, because there's so much iron and such low pH that all the iron stays in solution and it dissolves. So this is a major source of acidity, and it's a really common water quality problem because pyrite gets blown up as part of mining ore, and then it dissolves in solution and makes a really low pH system. Finally, we also have acid rain. So this is the SOx and NOx. We've talked about this already in class. Basically, these are emissions from coal-fired power plants and gas and cars. And again, this is the source of the sort of, at least the sulfur molecules, is related to fool's gold. So we have a bunch of dissolved sulfur molecules in our coal, and when we burn that gets volatilized into the air, and then it dissolves into water, and again it forms sulfuric acid in the case of SOx and nitric acid in the case of NOx. And this is sort of a major environmental impact that has been around for a really long time, but it's also one of those positive environmental stories that basically we found out about acid rain being a major problem sort of in the 80s, and we adjusted the Clean Air Act, and it's had a really major positive impact. So we can sort of check out the USGS real quick. And we can use their little sliders here to look at, this is the sort of hydrogen ion concentration as pH throughout the nation. So red is really sort of a low pH, and this is 1985 on the left, and then when I slide it over here, it's 2018. And you can see basically rain is far less acidic now, and that's because we added scrubbers and other technologies to our coal-fired power plants and other fossil fuel burning to reduce the amount of SOx and NOx that made it into the atmosphere. And just to show you that this is tightly correlated with the amount of sulfur in the atmosphere, this is sulfate ion wet deposition. So this is again 1985, and then if we scroll over here, it's 2018, and you can see that there's a lot less sulfate in the air too, and those things are directly related. So that's it for today, and I'll see you soon.